Hello, everyone, and welcome to the first conversation on Chapter 6. Chapter 6 is going to be a little bit different from anything else we've talked about so far. It focuses heavily on the integral, and primarily it covers a handful of applications that one might typically encounter for the single variable integral. Notably, since the integral talks about adding up a bunch of things, the so-called area under the curve, a lot of the applications we're going to talk about are applications to adding up a bunch of a quantity. Usually what this means for our purposes is we're going to extend into 3 dimensions, and we're going to talk about volume. And then toward the end of Chapter 6, we'll also talk a little bit about arc length, and then we'll talk about a physics concept known as work. But we'll get there in due time. We start in section 6.1 by introducing this notion of volume, which is essentially just 3-dimensional area. And we introduce not 1, but 3 different ways that we can visualize how we can use integration to compute the volume of 3-dimensional objects. Of course, we can't do this for any 3-dimensional object necessarily. In order to use these types of techniques, we need to have convenient 3D objects. And we'll look at a few examples before long. The first process that we're going to discuss is going to be known as computing volumes by using cross-sections. More or less, what this means is that we're going to take 3-dimensional objects, we're going to look at 2-dimensional slices, and we're going to add them all up. And this is going to be eerily reminiscent of what we did when we talked about Riemann sums. So we're going to take our 3D object, chunk it into a bunch of infinitely thin pieces, compute the individual areas or volume contributions, and then we're going to add them all up. So, for example, if I were to draw the following picture, suppose I have a right cone, and if I were to draw this in 3 dimensions, I might have my 3 axes right here. And suppose I have a cone that's on its side. So over here on the right, that is going to be its face. And then we have that the cone extends down and to the right like this. If this is my x-axis, and my y comes out the page and z goes straight up, this is my origin at 0, then the important takeaway from this setup that we have right here is that at any given x value, like, for example, right here, if I were to slice this object at that x value, so go ahead and do a nice horizontal slice as if you had like a table saw, the resulting cross-section would look something like that disk. And if you'd like to use those dotted lines in order to illustrate a circle, that works just fine. We could have done that up here as well. So solid line and then a dotted line. But it really, if I vary that x value, like if I put an x value here, its cross-section looks like that. And if I put another cross-section over here, there's x, my cross-section gets a little bit bigger. The idea behind volume by cross-sections is that at any single juncture, if I look at the volume contributed by that associated cross-section, that volume of that infinitely thin, in this case, of infinitely thin looking disk of some sort, well, an infinitely thin volume is just an area. So, for example, if I want to turn around and find the area of that slice, the associated area for this is going to be, well, it's going to be dependent on that x value. So the area is some function of that x value. And if my overall volume here starts at 0 and maybe the height of my cone is, I don't know, a 4, then what we're going to do is we're going to define our volume over here on the right to add up, i.e. integrate, all of my x values, so I'll use a dx integral, from 0 to 4, and in particular, what am I adding up? The individual area contributions, a of x. So the volume of this object is going to be this integral. But the important hard part of this entire procedure, as I noted in the following sentence, is that the hard part is actually finding a nice formula for a of x. That is really difficult. Finding that formula, which here, for example, my slices are just disks, so maybe we understand how to find the area of a circle. We'll revisit that in a little bit, that notion in a little bit. But finding that is pretty hard. We're going to look at two examples where we know what the sort of underlying geometric shape is, and then we'll look at another method that uses this technique, and we'll see how we can compute volumes in exactly this way. So we'll start with, admittedly, a little bit of a challenging problem, but it's one that is based in antiquity. And what this is the volume for a square pyramid. So this is find the volume of a pyramid whose base is a square with side length L and whose height is given by h. This is a question that was asked a long time ago since ancient Greek antiquity, and now we're going to provide an answer to this using calculus. In fact, based off of this discussion up here, this idea of turning objects on their side to slice them as if it was a table saw is exactly the type of picture we're going to want to draw right here. So let's draw a picture here because that's the most important part of this entire thing. And I note that right here. A picture is oftentimes the most helpful item. So let's draw a picture up here in the upper left-hand corner. So we're going to have some axes. So we're going to have the z-axis, we're going to have the y-axis, and the x-axis. We are going to have a square pyramid on its side. So that means over here we're going to have the base of the pyramid. Nice square. And it's going to have some point on the x-axis, much like the cone did up above. And so as a result, I can draw straight lines. Oop, that's not super straight. Straight lines to the tip of the cone. And there's my right. This is a square triangle dumped on its side. And much like the picture up above, I want to compute the volume here using cross sections. So I'm going to let, in this case, I'm going to let my independent variable be x because that's the slicing that I see here if I were to slice this with vertical cuts. Technically speaking, you can slice in any direction. For example, don't draw this, but if I wanted to slice on the y-axis, I could have. Then the corresponding slice would look something like this. But instead, I'm going to slice on the x-axis so that the corresponding slice, very importantly, is a square. That's the most important part here. So the bottom one comes up like this. There we go. So the slice there looks a lot like this. We'll get a slice out here, slice in there, and that right there, highlighted in red, is exactly the slice that I have of the pyramid if I were to slice it on the x-axis. And so, much like the picture I had up above, if I want to compute the area of this, that's going to be important. So here, I'm going to let the area of this be some function of, say, x is the question. And then in particular, it says here that the volume, let's see, the side lengths are L. So that means up here, the base is length L, and the height is h. So that means if I start at the origin, the height is h on the x-axis. And if I'm going to draw more pictures here, but the idea here is that volume, using the notion of cross-sections, should be the integral from 0 to h of this area function dx. But as I noted before, this area function is the hard part. I don't know what a of x is. I need to do more work to figure out what that area is dependent only on the x value. Well, usually this requires you to look at your picture and think carefully along geometric lines. For example, I might look at this and I might say, you know, that x value is between 0 and h. If I were to take this entire picture and I were to slice it horizontally, then I might be able to find a relationship between 0, h, and x in a controlled way, maybe even L here. Let me find out. So over here, what I'm going to do is do the following. I'm going to draw a horizontal slice. So I'm going to switch to, now pay attention to the way I label these axes. So I'm going to switch to an x, y axis. And if you compare and contrast the picture on the right and the left, that means that the horizontal slice through the xy plane of this 3D object is going to look, for example, like this. This is going to be my h value. I have a triangle coming down here. And technically, I have another slice over here. There's my base triangle. And I know, for example, that this length right here, only on the right, is L over 2, because the entire base is 2. So the idea is that the red slice that I've drawn over there is an x value right here. I said pay attention, and then I mislabeled it. This is not x and y. I have it backwards. So this is my x-axis. This is my y-axis. So my red x is the vertical x. That's going to be slicing in exactly this way. And what I can observe at this juncture is the following. If I look and zoom in on this picture, I'm going to put this in green. What I can observe is, let's look at this point on my red slice. So this is the point connected to x, yes, but it's more importantly the associated y value for that x value. And the reason that's important is because if I look at just that sort of picture, then it turns out that this red square, that length right there, is also y. What that means is that the area of this entire red slice is actually 2y, which is the entire side length of one of those red slices, quantity squared, because that's the area of a square, is the side length squared. So the area slice, a of x, is actually 2y quantity squared, looking at the picture that I've drawn here. So somehow I need to go from y and patch that through to the x variable. But now if I teleport over to my 2D picture here, the y value I just drew is exactly this y value on the y-axis. Well, what I've drawn here, if I look explicitly and only at this triangle right here, if I look only at this triangle, what I've just drawn is a set of similar triangles. Because if I were to take that picture and I were to zoom in only on that triangle, what do I have? I have that this length is a y. I have that this length on the bottom is L over 2. I know that this length right here is my x value. So therefore, if my overall height from top to bottom is my h, then the height of the upper triangle should be h minus x. So, since both of these are right triangles and one is nested inside the other, these are similar triangles. So by similar triangles, I know that the short height, h minus x, is to the total height as the short width is to the large width. And so if I take this equation, I go ahead and cross multiply, I'm getting L over 2 times h minus x is equal to YH. And then I go ahead and solve for y. Y is given as L over 2h times h minus x. And if I were to distribute that, what I'm saying is that y is equal to L over 2 minus Lx over 2h. And since, notably, the L and the h are both constants, this is now y given in terms of x. So if I zoom out and come back to the original problem over here on the left, I needed a formula in terms of x, but I only had one in terms of y, and here is a formula telling me how to compute y in terms of x. So it turns out that down here, if I look at the volume computation, the volume is the integral from 0 to h of a of x, which I know from upper left is the same as 2y squared. But apparently, that's equal to, if I substitute in y, I'm getting the integral from 0 to h of L minus Lx over h quantity squared. Where now I just have to compute this integral, remembering that L and h are constants. So this is going to be the integral from 0 to h. After I FOIL, I'll get L squared minus 2L squared x over h plus L squared x squared over h squared. Integrating all this with respect to x will give me L squared x minus, well, the 2 will cancel, so I'll get L squared x squared over h plus L squared x cubed over 3h squared, all evaluated between x equals 0 and x equals h. Of course, plugging in 0 kills the entire thing, so this is just going to turn into L squared h minus L squared h squared over h plus L squared h cubed over 3h squared. And let's see what that turns into. I get L squared h minus L squared h plus L squared h over 3. So those two terms cancel. And my final answer is L squared h over 3. And so if you were to pause this video and go check out Google, and you were to Google what is the volume of a square pyramid whose base length is L and whose height is h, it's going to be this formula. So the entire technique here is draw an appropriate picture, slice it, draw a 2D picture, and then try to understand how the variables all play together. That's the hard part. Because if I change this out for an actual cone, like I did up here, the procedure is identical. The only difference is this square is replaced with the area of a circle, for example. But it's completely possible and completely manageable. So let's do another example, because volumes by cross-sections require you to think critically about how things look, and I want to do at least another example so you can see a couple of of the types of problems you might encounter. So for example here, it says find the volume of a solid whose base is a disk of radius r and whose cross-sections are equilateral triangles perpendicular to the y-axis. So let's draw a picture. So over here on the left, I'm going to have my 3 axes. This is again x, y, z. The base is a disk, and now here again I need to make a choice. Do I turn this object on its side like I did previously, or do I leave it pointing straight up? It's actually entirely up to you. You can solve the problem either way. Maybe for this problem, I'll choose to leave it pointing straight up, which is perfectly fine. What you'll see is that the choice of doing that means I'm going to have a dy integral, not a dx integral, but that's fine. There's nothing wrong with that. It's just a different variable at play. So I'm going to put the base now on the floor. So we're going to put, let's see, I have a base that is a disk of radius r. So there is my disk of radius r on the floor. And the cross sections are, in particular, perpendicular to the y-axis. So if this is the y-axis, the slicing should be perpendicular to it. So that means the slicing should go horizontally like this. So let's go ahead and do that. So if I look in this picture, I'm going to have a slice here at a y. So the slice is an equilateral triangle. That's what's being noted right here. So when I slice at that red triangle, or that red point y, I'm going to get an equilateral triangle like this. So for example, if my y value was a lot closer to the edge, my equilateral triangle would have been a lot smaller. But as it gets closer to the horizontal x-axis, my equilateral triangle gets really large. So because of that, let's go ahead and keep ourselves a little simplified. Let's go ahead and not worry about all these other equilateral triangles. Let's focus on the prototypical one I drew right there in the middle. So that means I'd like to find what the area is of just that triangle right here. And because this started with a y-slice, it stands to reason that the area here should be dependent on a y variable. So I can determine, at least at this juncture, that the volume, whatever that's going to be, is going to be some integral of a y variable, where the area of this slice is given as a function of y. So that's going to be an a of y. We know this is a disk of radius r, so I'm going to move r units in the y direction, and in particular, r units, negative r units, I should say, in the negative y direction. So this y value will trace everything between negative r and r. Or, due to symmetry, you could simply go from 0 to r and then double it. But I need to find a formula for a of y. That's what I need to do. Well, much like the previous problem, it's useful to reduce the situation to a known 2D picture. Here, the only known 2D picture is going to be this circle or this triangle. And in fact, I'm going to draw pictures of both in due time. Let's start by just focusing on this circle here. Let's look at that 2D picture. So if I focus on just that, I'm now focusing on, it would appear, the x and the y axis. So let's put the y here, for example, and the x here. The circle in question looks a lot like this. We know it's of radius r. The y-slice has been chosen over here on the y-axis. So what that means is that this distance right here is y. We'll put on the bottom maybe. This distance is y. Much like the previous problem, it may very well be useful for us to note what these other quantities are. For example, I need to know, if I come over here on the left, what is the area of an equilateral triangle? Well, that might require us to investigate the triangle a little more. Let's draw that triangle over here. I'll do it in red so that it's a little more clear what picture we're drawing here. So there's that red triangle. How do I compute the area of a triangle? Well, I do know a couple things about an equilateral triangle. For example, I know that if I slice it in half, I get a 30, 60, 90 triangle. So, I'll do this in green. If I happen to know this length, for example, then I can use the relationship between a 30, 60, 90 triangle to find the area of the, well, then I'll have what? 1/2 base times height. So I'll have 1/2 the entire base, which is twice this green variable, times height, which I could find by the 30, 60, 90 relationship. So I need to find this green number. But on this picture, let's see, what is the green value? The green value is, say, equal to this value on the big picture. But what is that on the 2D picture in the middle? That's this value. But what is that if not the associated x value? What I also know is that this point is on the circle centered at the origin with radius r. So therefore I know that this is the point centered at xy is equal to, well, given a y coordinate, I can draw this radius r, and now I know this is the x and that's the y, and I know that this is a 90-degree angle, so I can use the Pythagorean theorem to observe that the x coordinate in this case is going to be equal to the square root of r squared minus y squared, and the y coordinate is just y. So in fact, it turns out that that's exactly what this green value is, the square root of r squared minus y squared, which is this value down here, the square root of r squared minus y squared. What that means is that the height is equal to square root of 3 times the square root of r squared minus y squared, because it's a 30, 60, 90 triangle, so that's from trigonometry. What that means then is that over here on the right, the area is equal to 1/2 the base, which is twice that square root object in the bottom, 1/2 base times height, which is now the square root of 3 times the square root of r squared minus y squared. This will simplify into simply the square root of 3 times, without the square root, r squared minus y squared. So therefore, the original formula that I was trying to find, what is a of y? Well, now we have the integral from negative r to r of a of y, which is the square root of 3 times r squared minus y squared dy. And that's some number. I don't know what the number is there. I can maybe leave those details for you to take a look at. The important part is getting here, because this is the part that requires careful thinking, the problem solving, and the drawing of a nice, careful picture along the way. So volume by slicing, when your slices are arbitrary objects, in this case an equilateral triangle, in this case a nice square. There's other versions of this where instead of equilateral triangles you have an isosceles triangle. Technically you can do this if you have like a regular polygon, like a pentagon or an octagon. Really anything where classical geometry and a little bit of trigonometry can tell you what those areas are if you draw detailed enough pictures. Which allows me to also note that if you were doing this on, say, an exam, the drawing of really detailed pictures is a fundamental part of this entire conversation. Having these pictures is where all the credit's at. Without these pictures, you can't really get anywhere. So keep that in mind. Oh, another one that I could do is, in terms of variations on these problems, I could, and so here I said perpendicular to the y-axis. I could have used the x-axis instead. That's fine. Equivalent problem. Could have used semicircles instead of triangles. There's a whole host of objects from high school geometry. So this sets up this entire idea of taking volumes by cross-sections. Set up a picture, slice it, compute individual areas carefully, and then integrate it. That's the idea. Situations where finding the value of your area is a little easier is more or less what we started with here. When you're taking slices and those slices look like discs, the situation gets a lot easier to navigate. So much so that that particular subcase gets a special name. And this is known as finding volumes by what's called disks, and as we'll see in a little bit, also by what's called washers. But let's start by talking about disks. So the disk method is specifically used whenever you're discussing the volume of solids generated by revolving a function's graph about a given line. This is very, very close, for example, to how pottery is made, if you want to think about it that way. So let me draw a picture for you over here. Typically, you're given some sort of a function. So here is a very typical looking function from Calc 1. What if I took that line and I revolved it around the x-axis? What if I revolved it around that? Then, for example, maybe it revolves into this sort of picture over here on the bottom. And as it revolves, suppose, much like clay on a pottery wheel, it actually traces out an object. Then what happens is that the area under the curve that you're typically used to computing, like, for example, if you were computing this area under a curve, then this entire area under the curve that you get from Calc 1, that entire region all of a sudden gets captured and then revolved with it. So it looks like maybe these dots need to come down a little bit more. There we go. And so when you revolve this entire thing, you get a nice three-dimensional object. And in particular, for example, at an arbitrary x value, the distance to the function, which we know that that distance right here is your f of x, that gets revolved into a disk, where notably, that disk, the area of this, is exactly the area of a slice of my overall 3D shape that I've built via a revolution. So I'm taking a function that I know, I'm revolving it much like a pottery wheel, and then the overall object that I get ends up looking a lot like, well, it has an opening over here, it has an opening over here, it has a starting value, A, an ending value, B, and the intermediate slices look a whole lot like disks. So in the spirit of volume by cross-sections, the area for this is some function of the x value input, and in fact, it's very easy to compute. It's the area of a circle, which is always pi r squared, but what's r? R is just the function value, depending on what that function is. So as a result, the volume is the integral from a to b of the a sub x, or a of x, which is the area function. So this is the integral, I should put this in blue, this is the integral from a to b of pi f of x squared dx. And this method is typically referred to as the disk method because the cross-sections look like disks. That's the fancy word I've been using. Much like we saw up here, it is possible if your disks and your slices are moving in the y direction, it is possible that your volume formula is given as a y integral. That can totally happen here as well. If I happen to take a function that's focusing in the first quadrant, for example, and I revolve it around the y-axis, then I would end up in a situation where I get a y variable as my differential operator. So let's look at some examples of this. So the first one, and all of these are going to require us carefully drawing a picture in some capacity. So the first one says, draw the following region. Draw the region between the curve y equals square root of x. So let's go ahead and draw square root of x So that starts here at 0, and it extends up to the right like this. This is y equals square root of x. Specifically trapped between 0 and 4, so let's suppose 4 is right here, and the x-axis. So the region that I'm revolving is this region right here. Here I'm coloring it in blue. You can do orange, you can do whatever color scheme you feel like doing, that's fine. So this region in the first quadrant is going to get revolved. Apparently I'm going to revolve it around the x-axis. So when I do that, I'm going to get a shape that's going to extend, for example, down here. Whoops. So when I turn around and I revolve around the x-axis, I'm going to get a reflected shape down here, a reflected ending point at 4. And so the overall shape is this bowl that's going to get built. And you can add as much detail as you feel you need to. So for example, I would get something that opens up like this on the right. So this is a nice little, I don't know, it's a top on its side. I don't know how you want to think about this. But if I want to compute this volume, since I revolved around the x-axis, so the idea here is that revolve around x. So that means my integral is a dx integral. Let me rephrase that. When I say revolve around x, what I really mean is revolve around horizontal line. That's what I really mean. So the x-axis is a horizontal line. So that means I have a dx integral. What that means is I take an arbitrary x value, I look at the associated radius, which I know is the square root of x, because that's the function value. I look at a disk at that point, and then I compute the area of that disk that I have right here. The area of that disk is always given by pi r squared. So in this case, it turns out that the area for this, which is what I'm typically going to call area here, is a of x. So here, the volume that I'm looking for is the integral from 0 to 4 of a of x dx, which is the integral from 0 to 4 of pi r squared, where r is the square root of x. So I'm getting the integral from 0 to 4 of just pi x. And if I go ahead and do the integral and evaluate it, I'm getting 8 pi. So here I've computed the volume of the subsequent object I get when I revolve square root of x around the x-axis. But you'll notice I did switch to horizontal line instead of calling it an axis. And the reason for that is because it's possible to revolve around any line that I choose. The next example will showcase exactly that. Here I want to find the volume of a solid generated by revolving, again, square root of x, but now I'm looking at a different region and revolving it around a different line. So let's take a look. Here I'm still working with the square root of x, which looks the same as before. So this is y equals the square root of x. But now I'm looking for the region bounded by the following lines. Y equals 1. So this is y equals 1. And x equals 4. X equals 4. Looking at the picture, that is a typo. That should not say x equals 4. That should say x equals 0, so that we're in the first quadrant. So this is our x equals 0. So it should be this region, bounded by the y-axis. So this is the y-axis. And those lines. So as a result, the region that I'm going ahead and revolving is going to now be this region, which is nowhere near the x-axis. And in particular, I'm revolving around the line y equals 1. So as a result, I'm revolving around this line. So the object that I'm looking at, this shaded region, gets reflected around y equals 1. So the actual object that I get, well, up here at 2, I'm going to end up getting something that comes down and touches at that point. So what that means is that my arbitrary x value has a disk, well, a disk that now moves left and right through this sort of cone-looking shape. But as I saw here, if I revolve around a horizontal line, which I am right here, again I have a dx integral because my slices are chosen with an x variable. That's the pattern. Note that the square root of x hits a 1 identically at 1. So this point right here is at 1. This is my x-axis. This is my y-axis. So as a result, if I want to find the volume of this disk, well, I need to be a little bit more crafty. If I look at this, the volume is not actually the radius. Well, let me be careful here. That sentence makes no sense. The radius is not the function value. Here, the radius in question, I'll put it in pink, is this value. So let me actually redraw this and zoom in a little bit. So if I look at this disk right here, here it is, there's my x value. The radius I'm looking for is this. But what is that value? Well, I do know that the value from the x-axis of x up to the function, I do know that's the function value. And I know that this distance is a 1. So the pink value at the end of the day really should be 1 minus the square root of x. That's my radius. So what that means is that if I want to compute the area, I should say, of this overall disk, the area of that disk, which I'm going to call a of x, really should be pi r squared, where the r is 1 minus root x. So it's not actually just the function value. I really do need to draw a picture and interpret it appropriately. But once you appropriately interpret it, here I can observe that the volume in question, using the disk method, really is just the integral from 0 to 1 of a of x dx, which I see now is just the integral from 0 to 1 of pi r, which is 1 minus root x, squared dx, which is some number, but the main idea is setting it up. So what we've observed here is that if I revolve around a horizontal line, I should get a dx integral, and that my radius really needs to be carefully drawn using the pictures that I have at my disposal. And so much like with the volume by slicing, not having a super great picture is going to be to your detriment. But what happens if I revolve around not necessarily a horizontal line, but maybe a vertical line? What happens then? Well, we can predict that instead of a dx integral, I'll end up with a dy integral. And as a result, these disks should probably be, well, instead of moving along the x as vertical disks, I'll probably be moving them up and down as horizontal disks. And that's exactly what I'm going to get in the next one. So here I have find the region bounded between two different curves, interestingly. So here I have, well, let's find out. Let's draw y equals x squared. Now I do want to be, I'm reading ahead a little bit, I am focusing in on the first quadrant. So looking at y equals x squared, that's this parabola. This is y equals x squared. y equals 2x is just a straight line, mx plus b, so it's starting at 0. There I am. So this is y equals 2x. This is y equals x squared. And I want to revolve this around the y-axis. So this is revolving around the y-axis. So the region in question, I'll highlight in blue for example, is this small wedge. And I would like to revolve that around the y-axis. And interestingly, something different will happen. I'm going to get a reflected copy of this stuff over on the left. And what I see here is that I'm going to get some sort of a massive sort of, well, what do I get? If I do this revolution around the y-axis, kind of looks like I get a little bit of a bowl shape. I seem to be getting, for example, with an arbitrary y value here, the actual blue shape that gets revolved seems to have, for example, some sort of an inner disk, but also some sort of an outer disk. So the contribution coming from this slice really is some sort of, well, it's not really a disk anymore. This object is kind of like, well, I don't know what kind of physical object you'd want to use at the current moment. I don't know. I think the way I like to think about this is that this object is kind of like two disks. It looks like a big disk minus a small disk. And in fact, maybe that's one way we can think about this. Maybe what we can do is we can compute the volume as if we had a big disk, and then therefore we don't have a bowl at all. And then maybe we can subtract off the volume of whatever the bit we need to core out is in order to get access to the eventual bowl shape. So the picture that I want to think about here, so when I think about this, I'm going to write this as an area here as a function of y. The picture that I have in mind is that this looks a lot like some sort of a circle within a circle. So that's the sort of top-down view that I have in mind when I look at this picture. I have a disk within a disk. So the way I'm going to think about this, maybe I'll move this picture over here. The way I think about that picture is that that's the same thing as the overall area of the big disk minus the inside disk. And so that's the way I think I want to think about this. Is it's going to be the big area minus the little area. So what that means, if I were to draw this in maybe green, is if I know what this radius is and I know what this radius is, then the radius I'm kind of looking for is, well, maybe I can give that a name. Maybe I'll call this big R, call this little r, and then this is going to be big R minus little r, for example. So I'm going to use the disk method on the big disk, the disk method on the little disk, and then look at some subtraction. It's probably worth noting that if I were to ask when, so what the y values seem to start and end at 0 and whatever this value is. Probably need to know what that y value is. I can find that fairly easily by setting these equations equal to each other. If I set x squared equal to 2x and I solve, I'm getting x squared minus 2x equals 0, which means x minus times x minus 2 is equal to 0, which means x is equal to 0 and 2. So that means my y value is equal to 0 and my y value is equal to 4. So that's my 0 here. This is 0, 0. And then this is the point. It looks like 2, 4. So I can tell right off the bat that the volume here is going to be, it's a dy integral, and it's given an area of this little circle minus a circle, and I'm integrating from 0 to 4, it would seem. And the way I'm going to think about this is I'm actually going to take the volume of the big circle minus the volume of the little circle. So I'm going to think of this as the integral from 0 to 4 of pi big R squared minus pi little r squared dy. But what are those equations? Well, I can just use the actual equations given to me, and I can just solve for the other variable. So, for example, the little radius here, I can think of that as getting to the first line. This is going to be x equals y over 2. And I can think of, we'll put in orange, the radius to the big edge is going to be x equals the square root of y. That's just by taking these highlighted equations and then going ahead and solving for the other variable. So here I'm going to end up getting the integral from 0 to 4 of, well, we can pull the pi out probably, of big R squared, which is square root of, sorry, that should be the square root of y. So this should be the square root of y squared minus little r, which is y over 2 squared. And then you can expand those and solve that. So this object right here, this problem we did here, not only showcases that you can integrate with y variables instead, but this also showcases that you don't have to restrict, like we did in the previous two examples, to slicing by only disks. Here we get solid objects. But if I want to build like a bowl or something with my pottery, like I have here, then it's sufficient for me to look at this and say, okay, what if I just do one disk and then subtract another disk method? If I do both of those back to back, then what I end up getting is a bowl. I take some sort of existing shape and I core out an inside. This object, and especially like this one, if I look at in the bottom left, this little picture I drew in the bottom left, if I had to think of a physical object that this looks a lot like, one thing you could think of is it looks a lot like a washer, like the washer you would use in construction in order to put around some sort of a screw and things like that. So as a result, this technique that I just did in this problem really is called the washer method, which, as we saw in this problem, is actually just the disk method, but twice, and then you do some subtraction. And so that becomes sort of the premise for the remaining examples of this conversation, is using the washer method to just compute more areas, i.e. more volumes of 3D objects. So in the next video, what you're going to take a look at is a formal introduction into the washer method, and there we'll reiterate some of the concepts that I just laid out here, but I'll write it out in a more general formula, and then we'll look at a handful of examples that help make this concept make more sense along the way. So enjoy the rest of that second video. If you have any questions, be sure to let me know, but otherwise, enjoy the rest of your day.